Hello.
Hello.
How are you?
Okay, so this is 5.1, this is the second part of the notes of Calculus 1. Yesterday on the previous notes we actually did part A, part B, and today we're gonna do part C for the same function. 0 to 10 using lower bounds with sums of rectangle. So yeah. Okay, so what we're gonna do that are under the graph. Okay, so in this case, under the graph are all going to be the left-handed intervals. So as I make my little rectangles, it's always left hand here. So when we did yesterday's, we found out what's the first thing I have to start this out to do these rectangles. Yes, so that would be what?
1 or like
Okay, but let's set it up. Let's set it up, please.
0, 1, 1.
Oh, I know, but there's like a step that we do to find it. How do I find it?
B minus A over.
There, very good. Okay, so it's the B minus A over N. So in this case right here, the B minus A over N, so my upper bound, which would be 10 minus 0 over, this one's going to be 10 subintervals, so it's 10, I put N, and even underlined it, 10, which gives me 1 as my sum intervals. As I'm doing my function right here, I know it's going to be 1 times whatever f of x is, right? 1 time. So it's just like what we did on the warm-up here, but what can I do with that 1? 1 times anything is itself. So if 1 is going to be the width, it's just going to be the f of x that I'm adding together, right? So f of x of my interval. So let's take a look at my interval. So I'm going to start off over here. So my interval would be from 0 to 1. 1. Interval from 1 to 2. 2 to 3. 3 to 4. 4 to 5. 5 to 6. Come on now. So 5 to 6. 6 to 7. 7 to 8. 8 to 9. And 9 to 10. Alright, now that I have my interval set up, it's always going to be, for this case, being an under, it's going to be a left-handed. So for this case, it's going to be f of 0. So my function is right here. So I'm just basically plugging in here. So f of 0 is going to give me, say 0. 0 plus f of 1, right? Because in each of my intervals, I'm going with the left-hand side for each one of these. Right here, because that's the width of each rectangle for each interval. So my left hand is the left number. My right hand would be the right number. If I was going to do a midpoint, what do you think I would do there?
Go in between.
Divided by 2, right? So it would be my left plus right divided by 2, right? Okay, or left. See what I did there? Okay. So 1. So f of 1 is, say 1.
1.
Plus f of 2.
4.
Plus f of 3.
9.
Plus f of 4.
60.
Plus f of 5.
25.
Plus f of 6.
36. 49. 64.
Hey, don't kill my vibe here. Seriously, I'm not. Come on now. Where's that? So, f of 7.
49.
F of 8.
64.
F of 9.
81.
And f of 13.
169.
Okay, so I'm just making sure you're paying attention. All right. Okay, so f of 10 is 100. There we go. Now it's just the sum of all those intervals. I said that just to see if he's paying attention. He just... Why we what? So. All right, so on this one right here, thank you, in my audience, they said, why did I do 10? Is 10 part of my interval? No, it's not. So as we're going on this, we have to make sure that we're always only going to include the left-hand side. So for the last interval, that means that even though I'm going all the way to 10, I stop at 9. Okay? So you guys have to make sure you guys are paying attention to that. I was going to keep going all the way out, but a lot of people make that same mistake right there because it says going from 0 to 10. Everyone wants to stop at 10. They want 10 to be the last one. But in my interval, my left-hand side, 9 is going to be the end here. Okay? Does that make sense?
Yes.
Okay, good. That's what I'm trying to get at. All right, let's go ahead and add those bad boys together.
285.
What do we get?
285.
285. So my area,
Units squared.
now, why am I doing this? What is the reason for this?
Because math.
Because math. That works every once in a while.
To find the closest area of the graph.
Okay, but why do I want to find the area? What that does this have to do with anything?
Oh, because the area is
Yeah. No.
like
Stop that.
depends on what the graph is. Like
No.
for example, if it's an XC graph, we can find velocity knowing the area. Or
Okay, so now here's a better. Okay, this is gonna go ahead.
Is it because later on? Because like later on, what we're doing in the other chapter, it's all just a mess. You know?
Yes, it is a mess. It is, but knowing why we're doing this and what does it mean is going to be beneficial and like helpful for you later on.
Extremely.
So let's pretend like this is a function of distance over time. Okay? Distance over time. So that's going to be in blue. So it's going to be S of t equals, okay, I'm changing this right here to t squared. Where t is in seconds, all right? So, let's take a look. So as I'm doing this, S represents the what? Say position. My original function is the position, right? So it's going to be where are you at that many seconds, right? So if we throw a ball up in the air, you know, whatever the function is, right? So after t seconds, it's going to tell me where that is, right? That's important. But being a position function, we're going to have this. So watch this. So now from here to here, from here to here, being left-handed, I'm going there. Okay? So given that, okay, after 1 second, I am estimating that I have traveled how far? 0. Okay? Traveled 0. Okay? After the next one. I can't even see the graph very well. So that starts off at 20, so that makes that 10, right? And that 5. So the next one's going to be
Or
right here. So no, I'm looking at the one right here. So the next one is going to be here to here. Okay, so after 2 seconds, how far did I travel? 1. Okay, so together, it's 1, right? I have my position function. Okay, after 3 seconds, all right, there we go. Okay, after 3 seconds, right there. After 3 seconds, 1, 2, 3. How far have I traveled? 5, right? Okay, so I've traveled 5. So it's the total distance over time. So as I'm keep finding this area, okay, and so now I just keep going with it, here to here, and then here to here. Oh wait, too far on that one. There we go. Now, by finding all that area together, if this is distance over time, I'm finding the area under this position function, it's giving me the total distance traveled. Does that make sense now? Yes? So given this right here,
But it's not exact distance.
it's not, but it's, yeah. So it's an estimation of this. So, but that's what the meaning is. I'm trying to find that for that reason. This is the best application of this specific math that we're going to be doing. If you guys understand the reason, what we're doing it for, and why we're doing it, and what does this mean, that's going to mean so much more than, can you take the integral of here to here? Yes, I could do the numbers, but what does it mean? I don't know. I did the math, but you need to know why. For what reason? What does this give me? What does it mean out of it? So, definition, area under graph of function, okay, non-negative, enclosed, we get my delta x, which is my, okay, what I had right there, right? That's my delta x, that's the width of each of those rectangles, right? Say yes. Okay, good, yes. And so, as I keep doing that, as n goes to infinity, so think about it on my previous one. So here n is 1. What if I keep going bigger and bigger and bigger? If I keep going bigger and bigger and bigger, am I getting closer to the actual number? Say yes. I'm getting closer to the actual number. So I'm going to add more rectangles in there. More and more rectangles. So I would have another rectangle here. Okay, another rectangle here. So it's going to be less and less of my graph that is not shaded. So just keep going. I'm putting a lot more in there, so it's more and more. So that means less and less of the graph is actually not being represented. Now, as that's going to infinity, as n keeps going more and more and more, going to infinity, my delta x is what I was working for here. My delta x, that whole thing comes out to there because I'm going to take it to the limit as n goes infinity. That's the width, that's the thickness of my rectangles. That's the change in my x. That is the width of all of these things. We're going to start referring to it as delta x because in these terms right now, I'm thinking about it in the x-axis, not t's. If I had delta t, it'd mean the same thing. The thickness of my graph going left to right. We'll change it eventually to be up and down also. But at this moment right now, we're trying not to confuse you with that. It's just the thickness of this, my width of each one of these rectangles. Okay. Area under this, using upper sums. Okay, rectangle ascend above the graph. For this, delta x, okay, comes out to here, n over here, 10 over n. So, this one's going to be an easy one. Do you know why? Is it a straight line?
Yes.
It's a straight line. So this whole thing,
I mean, we can just try to get
yeah, over however many upper sums, rectangles extending above the graph. So no matter how many I put in there, okay, it's all going to eventually come out to be the area of that shape. What shape is that?
the triangle.
Triangle, right? So the area of a triangle is supposed to be what? 1/2 base times height.
Yes.
Okay, so my area formula, 1/2 base, which in this case is going to be what? 0 to 10 is 10, times my height, which is 30. So it's going to give me, area is 150 units squared. That's an exact answer because that is a linear function. We're eventually going to be messing with other things that actually are not. Yes, a lot of squiggly stuff. Squiggly line. Okay, so if I were to do this, let's say for instance, I'm going to block this off So I'm going to say here. So this is going to be under a graph upper sums. So the upper sums right here would be an overestimation. Like that. That would be another one like that. So this one having n be, what would my n be in that case?
5.
It'd be 5, right? Why is it 5?
That's because 5 is not.
I have 5 rectangles, don't I? 5 rectangles, so I get that. So it's possible to do this. Now, I guarantee you this is always an AP question. You're going to get something like a table or a graph, and it's not going to be equal sums. You just have to estimate it. So pay close attention to the wording, if it's equal sums or not. If it's a graph, then, you know, look at it, you can see what is supposed to be the thickness. And if it's a table, and they already have it partitioned for you, just go with it, because it's giving you left, right, and your function values. Same thing here. Area under a graph from here. Using lower sums. Which side would be my lower sums here?
Left. No, right side.
It would be the right side, right? The lower. So for a underestimation here, I want to use my right hand side, don't I? So no matter what I do, let's say 0 to 4. Let's see, this is. My pen's running out of ink.
Doesn't have.
Yeah, see what I did there? That was funny, right? I don't care who you are right there. That's funny. All right, so. So, there we go, right there. All right. Because the right-hand side, my right number at 4, my f of 4 is 0, right? So it doesn't look like it's a rectangle, but guess what? It's a rectangle with no height. So yes, it is still part of my partition. I think that one's it, yeah. Alright. Why is that weird? Oh, maybe I duplicated it by accident. Okay, it's fine. Does that make sense?
Yeah.
Did I confuse the crap out of you guys?
Yeah.
Most likely? Alright, good job. So, don't forget, like, share, and subscribe. This should be one of those things that just a bunch of algebra. That's all it is, a bunch of algebra. Don't forget notifications. Alright, video, if we get 500 likes, okay,
I don't make one.